a rather neat star-shaped LED lamp. This lamp has a square of glass in the middle of it, and on that it appears to have deposited 50 LEDs in series and then covered in a phosphor-loaded gel, and the result is that you end up with a star that lights very brightly, far too brightly, but it's this very bright star in the middle, and the power consumption is 3.5 watts, 26 milliamp current, 0.5 power factor. That does allude to a switch mode power supply, and I've confirmed this by putting a resistor in series of the lamp, a 220k resistor, and when I did that, if it had been a simple current regulator, it would just have dimmed down. But in the case of a switch mode power supply that has to sort of power itself as well as the lamp, it causes a cycling. It actually started pulsing like a strobe, and I shall show you that at the end of this video because I've recorded that bit already because I thought it was quite a nice effect, and I'll warn you in advance because there will be strobing at the end, but I will warn you when we get there. So let's investigate this lamp. So I would like to know what voltage is across this cob array. I'm guessing it's 150, but the best way to find out is to open the lamp like this. And once we've got all the glass out of the way, you know, that pesky glass, that isn't quite nice in its own right, isn't it? Let's bring the meter in and set it up to about 200 volts here. I'll just brush some of this glass tenderly out the way. There's lots of glass over my bench now. And we'll measure the voltage across this. Now, that side says positive, that side says negative. It's quite nice that the cob is marked in that way. Someone suggested I could stick a bag over it, not to contain the glass, but to see if there's a vacuum or a positive pressure. 135 volts is what it's showing. Can you see that? 135 volts across that. Or thereabouts. But they thought that if I put a bag over and it sort of puffed up, it would have been under pressure inside. And likewise, if it had sucked in, there would have been a vacuum. But I doubt there'd be a vacuum because the vacuum offers thermal insulation, and you don't really want that with a LED filament. So let's gingerly get the shattered remnants of this out without cutting myself. That could be the tricky bit. Where's my long nose pliers? Long nose pliers. And then we shall, that's a pair of snips. That's not a pair of long nose pliers. They don't even look like long nose pliers. Where are they? There. So let's just tenderly get this out of here. Oh, more broken glass. Oh no. Ew. And then, actually, you know what? I might pause momentarily to clean up this broken glass because there's slightly more broken glass than I was expecting, but that's okay. One moment, please. Okay, I think that's most of the glass up, and no blood yet. That's a good result. So I'm thinking I may actually just cut this off. There are solder pads in this, but it looks as though they'd be quite easy to damage. I'm not really sure about that, so I'm just going to cut this off. Actually, tell you what, let's mark which side's positive. That side is positive. There we go. And it's already marked on the circuit board. So I shall now very carefully, is this going to damage this? Is it going to put stress in it? No, it's come off quite easily. And we've got that bit off. I have to say, smashing LED lamps is surprisingly gratifying. They make a really nice noise when you break them. Now, as a precaution, I'm going to be all safety. I'm going to actually put a glove on. I know, it's not my normal behaviour, but there is broken glass here and I'm going to be nibbling around here. So let's nibble this open and get into here. For those wondering, it's Port West gloves. Quite like these gloves, actually. This sort of grappling, you could punch people with these, they're quite good. They're not really intended for punching people with. Except Carillion Safety Management. Oh, did I mention Carillion? There's a thing going on in the UK at the moment. A company called Carillion has kind of gone into sort of receivership or whatever, and it's a bit of a, yeah, they've got a bit of a history. I've worked on their jobs before, and I have to say that if they go bust, it won't be a bad thing. I'm sure that all the technically skilled operatives that did work with them will find new and better jobs. Hopefully not their safety management, who were the most arrogant, most malicious, axe-grinding little midgets I've ever come across. Just really to the point, that's, largely the reason I stopped working in the construction industry back when I was working their jobs was because they were just, you went to work and it went from being a nice experience going to work. I used to love going to work on construction sites to, on those particular sites, just being unpleasant. Not every site, just the ones that Carillion ran for some reason. They seem to have this strange, aggressive policy. Red tape and politics. Well, politics, very good description. Oh yeah, let's see what we got here. I'm seeing a small inductor here. It's wrapped around with Kapton tape. I think any of you who have worked with Carillion may actually know exactly what I'm talking about. Or you may have had good experiences. I didn't. Oh, this is quite interesting. This is quite interesting indeed. Right, let's liberate this with that and that and try and get this little circuit board off. Is it held on largely by Kapton tape now? Yes, it is. So the wires are coming down at the side, so if I could snip those wires and get this tape off, let's try and unwind this tape. No, it's not going to unwind. There we go. Oh, it's a very, very simple little buck regulator. Right, I'm going to cut. Where are my little mini snips? Let's cut that wire and that wire and liberate all the broken glass and messy stuff out the way at the moment. This is the point I do normally cut myself when you're trying to sweep it across the table and a bit sticks in a rut left by a previous incident and then stabs you. So what we got here? We've got the power coming in. Can I fold this out the way a bit further? I could fold this out the way a bit further if it's wanting. No, it's not wanting to fold. There it goes. Got the power coming in. We've got a little 8-pin chip which should have a number on it because it looks like a conventional regulator. Interestingly, we've got, let's zoom down in this a little bit. Zoom. Is that in focus? I think it's probably relatively in focus. Interesting features. They've got pins here that look like standard header pins, and that's what they've used to wire wrap onto the actual wires from the lamp itself. The chip itself that's doing all the sort of technical work, can I read this? Can I read it? I'll read it first, then I'll let you have a wee look. Oh, maybe I won't. Maybe I'll just pause. It looks like an LIS 84 something something something. Now, I think I'm going to have to clean that off because it's not that easy to read, even with the illumination on. You might have the advantage there, actually. You might have the advantage of a bigger screen to see that. The inductor here, it looks like just a standard inductor. I wonder if there's any feedback. I wonder if there is a feedback winding off that. There may actually be. Right, okay, tell you what, I'm going to explore this. I'll be back in a moment. A little bit of online detective work later reveals that this chip is clearly one of those special chips that's aimed at the Chinese market, not really the likes of us, because I couldn't find that exact chip. I could find this very similar chip, and that's good enough. So I've got my glass of blue-collar trash champagne, which is fundamentally cheap white wine, carbonated in the soda stream to make it more exciting. And let us start reverse engineering this. So let's get rid of this bit first because it's quite easy to get rid of. The main supply comes in, and it comes in on these two connections here. It goes to a bridge rectifier, which is this surface mount bridge rectifier here, and then from there it goes to that capacitor, which is this capacitor here. Right, let's get that bit out the way. The rest of the circuitry is almost identical except for one rogue little capacitor here and one rogue little resistor here that I'm not sure. This must be a slightly different chip, but it doesn't matter. The bulk of it is the same. So the power supply for the chip is derived from a couple of resistors from the positive rail and a capacitor. Now, at the end of this video, I'll be showing that strobing effect, which is quite interesting. What's actually happening there is that I'm limiting the current and the voltage in this capacitor is rising up to the point that this chip then detects its start threshold and then it bursts into life. It lights the LED, but it pulls the voltage down in the electrolytic capacitor because the current's limited, and then it drops below the cutoff voltage, so this chip then shuts down again. Then it starts As soon as it's shut down, the current drops, so it starts charging up again. It does that repeat cycle, and you'll see it. It's quite an interesting strobing effect. So this is the power supply. It's two resistors, 18 and 4 zeros, so that's 180k in series with another 180k. And then there's a capacitor down here to the negative rail, which then feeds over to the chip, and that's this capacitor here, and that provides the power supply to the chip. The chip then drives the LEDs via this inductor. That's this largish inductor here, which does have 4 pins. I was actually going to turn the photo over there. That's not going to work, is it? The 2 pins at this side are common, and the pins at this side are separate, but only 2 connections are made. It's just they've put solder pads in them all for strength and rigidity. So that's the inductor. That's the diode there that equates to this diode here. The capacitor for smoothing across the LEDs and the resistor are these 2 components here. So this is the capacitor that's smoothing across the LEDs, and this is the resistor that's across that. I'm not sure if it's what the exact purpose of that resistor is. It might be to provide stability open circuit, or just to make sure that when it's turned off, it discharges out. You know, maybe I shouldn't drink blue collar trash champagne. I almost actually probed the picture. It's that good. Anyway, let's test across the picture. Oh, there we go, continuity. Let's not then. So there's those components there. They are in parallel. That's those 2 connections are checked. There, they are in parallel. There, that's those 2 are connected. They're connected to one end of the LED circuit. That's those connections. On the other end, I'm testing over to the other side. So I tested between that side to there. So that is the other part of the circuit. So that is exactly how it's arranged. And fundamentally, that's about it. This pin here is connected to the inductor. Oh yes, quite important one, the current sense resistor. This is a bit that determines how much current is going to flow through the LEDs. That's down here. I'm guessing this Chinese probably says it should be as close to these pins as possible. That's what they usually say. In this case, 5R60, 5.6 ohms. The R is used as the decimal point. So that one is connected probably between, I think it's between, where will it be? It will be pretty much to ground, won't it? Hold on, where is that? Where is that? It's tiny. There it is. That'll be connected to the negative rail, maybe. Yes, it is. And the other end will be connected to that pin. No, that pin, that pin. There it is. It's connected to, it seems to be connected to the 3rd pin up. This capacitor is connected to this pin. I'm not sure what that capacitor is for. Probably just some internal module in the thing. So that's it. It's very simple. It's very straightforward. It's a very typical of a buck regulator for an LED array. So now we could redesign this a bit. Let's see. I'm going to get the soldering iron on. I'm going to bring the notepad in. Now, the first thing I'm going to do is I'm going to try and solder onto this. I could just solder onto these pins, but I kind of want to solder onto the LED array itself, the glass, to see if it shatters, and that was a terrible idea. It's the only way to find out. I'm not even sure if that's a special solder. I don't think it is, but I shall be soldering with extreme caution. I shall put a couple of leads on like these. I've prepared them already. I'm just going to check the soldering iron is not tangled amongst all my tools, as it sometimes is, because that usually results in a huge avalanche when I grab the soldering iron. So here is what I've selected to do. I'm going to keep it simple. I'm not even going to use a capacitor largely because I couldn't find the capacitor I wanted. So what I'm going to do is I'm going to take the AC in and I'm going to put it through 2 resistors. The resistors are then going to go to a bridge rectifier. Let's draw it as an actual bridge rectifier then. So here is an actual bridge rectifier, full bridge rectifier, which you can add the electro boom sound effects yourself. So this is going to be the positive connection, this is going to be a negative connection in a bridge rectifier from the AC pins. The diodes all point towards the positive, so there's a diode pointing towards the positive, slightly squint diode, but that's okay, and there's another diode pointing towards the positive. Likewise, from the negative, they point away from the negative, all pointing towards the positive. And what a bridge rectifier does is When this pin is positive, it diverts through this diode here to the positive pin, but if it's negative, it will divert through that diode to the negative pin. And likewise the other pins, so that whatever polarity, it always comes out positive and negative. It's just a very simple gating system made possible by the incredible diodes, just that PN junction. It's very, very clever. The technology, I mean, how long ago was the diode invented? The solid-state silicon diode, just it's genius. So now I've got the positive and negative, current limited by these resistors. I'm actually going to connect my star, a really badly drawn star, between the positive and negative, and that will now, if this is a sine wave which has been rectified, it's only going to light from about, say, there over to there. So it's going to be a bit shimmery. This is probably going to be something visible to you, but not to me. It's the simplest bit of circuitry. The other option I could have done was the A plus and minus. I could have actually added a capacitor across that, electrolytic capacitor, to smooth that with a discharge resistor across it of a high value like 1 megohm, just to stop me getting a zing off that capacitor, because it would otherwise be charged up to the voltage of the LED array. So before I start this, before I even go anywhere with this, the first thing I'm going to try and do is desolder these existing pins and solder on new leads. I've just dropped something, that's okay, I do that quite a lot. So let's get some solder. Do I have some solder here? I've buried everything under paperwork now. I'm looking for solder, I'm not seeing solder. That is not solder, that I've dropped something else. It's an avalanche. One moment please. There's some solder. So I'm going to tentatively try melting this solder and soldering onto that pad. The glass is not cracked yet. This is a good result so far, but things could go horribly wrong. Let's try wetting that a bit more and see if the glass goes as it could do. So far so good, so let's tin this lead. Now that I've tinned those leads, and just touch this onto there, and just enough heat to flow it on without lingering too long in case something horrible does happen. Because I quite like that little LED star. I'm trying to think what I could use. It's not the sort of thing, it would be interesting having fair lights in your trees, like this, your Christmas tree, but the slight downside of that is that about 140 volts across that star, which would provide thrilling electrical experiences when you handled the ornaments. Right, I've soldered those leads on. They appear to have stayed on. That's quite good. Let's make the bridge rectifier. Let's get rid of these bits of wire which had actually stuck to the MDF by the power of solder. So, the resistors, like the maths, right? I've got 240 volts RMS, and I reckon the voltage across this is going to be, say, 140 volts, so I've got 100 volts to drop. I worked it out. I want to keep it within the rating of a couple of quarter watt resistors. So 100 volts, I'm going to go for, say, well, the two resistors I've chosen are 15K. I equals V over R. So that'll be the 100 volts to drop divided by the combined resistance will be 30K equals. So it's going to be about 3 milliamps, and that's going to be times 100 volts equals 0.3 watts divided by 2 equals 160 milliwatts, which is well within the 250 milliwatt rating of these resistors, and the LED star at about that 3 milliamps. That'll be fine, because keep in mind there's 50 chips in there. It's going to still be amply bright. I might be lying. We'll find out. Here are the first two diodes I'm going to use. I'm going to place them across like this. Let's zoom up on this just a tiny little bit, shall we? And then I'll try and actually stay in shot if you're very, very lucky. It might even be in focus. One day I will get my big monitor up top. So I'm going to twist them together, but I'm going to twist them together not hard against each other. And I've got the two bands pointing towards where I'm twisting, so that is going to be the positive. So let's twist that. That's the positive end. Now I'm going to get the next two diodes to make this rectifier. And I'm going to twist the negative end in the same way. So I'm going to overlap them slightly at a slight angle and twist them like this. It really is going to look like a bridge rectifier. Then for the other connections, I'm just going to overlap them like this. and twist them again, and these are the AC connections. Remember that the positive can be easily identified in a discrete rectifier like this by looking which way all the bands point, because all the bands point towards the positive. You may hear my stomach grumbling. I have eaten tonight. That I'm not sure why it's grumbling. It may be because I'm drinking Blue Collar Trash champagne. Talking of which, Blue Collar Trash champagne. It's so fizzy and trashy. Ideal for people who never really grew up. Now that I've twisted them together, I'm going to solder them. So I'm just going to solder them all. And then try and remember which ones are very, very hot so I don't grab a hold of them. So I'm going to solder that. And then I'll solder that. And, everything's getting very hot. Everything's getting very hot. And then this. Yep, it's hot, it's hot. That's fine. Asbestos fingers. Thick-skinned, it's an advantage. So let's crop these down a bit now, but leaving enough that as soon as I try to solder onto them, they don't immediately untangle. And the two bands here are pointing towards this lead, so this is the positive. So I'm going to solder I'm going to tin the positive of the star, and I'm going to solder onto that. Just going to solder onto, let's get the right one, shall we, having said that. I'm going to solder onto the positive connection. And likewise at the other side, I'm going to solder the negative lead after tinning it onto the negative connection. Will this work? Have I already destroyed the star? Dunno. Part of me wants to scrape some of the phosphor-loaded gel off the side that doesn't have the tracks, just to see the track layout under that. I may do that. You know, I may actually do that. Just to see what it's like afterwards, see what sort of pattern the tracks are, because obviously it's like a tiny little sort of printed on glass circuit board that will have all the LEDs deposited onto little pads. So that's the negative, and this time it's the connection that is complete opposite of the positive one, where all the diodes are pointing away from the negative. The AC ones will have both a diode pointing at them and away from them. And for those, I'll just leave these full length, these resistors, to give maximum length, because I'm going to be stuffing it into a quick block shortly, the quick test, should I say. The Cliff quick test, I noticed that CPC in the UK are selling a clone of the quick test. I'm not so sure I'm keen on that. It comes with the ominous warning that it's not for continuous use, so they may have underrated it somewhat. I don't like seeing British products copied. But then again, everything gets copied, doesn't it? So that's that. I don't like seeing American products copied, as you may recall from the Xuron episode, when I got a set of snips from eBay, cheap Chinese ones, and they were marked Xuron, and it turned out they were nothing like the actual Xuron snips, which are American made. Quite expensive, but just worth every penny, because I keep them for special applications, because they produce a really interesting cut. And that is my circuit complete. So let's pan back out here. So I've got my two resistors to limit the current, hopefully the correct value, otherwise this LED is going to be very bright and there's going to be smoke, which you guys want, but then it might not happen. Let's bring in the quick cliff test. Someone mentioned recently that how old is that plug? This is an old unit. I got this from work ages back. Let's open this and see if it's one of the original MK plugs. Yes, it is. The ones with the sort of thumb screw type things that clamp down the cables. I used to actually hate those because they were very annoying to terminate. I kind of prefer the ones that pinch the screws, but I can understand why these ones are a better idea in a way. Let's plug this in and let's ram these connections in here. So let's ram a resistor in there and a resistor in there, and is it going to light? Let's get that out the way, and keep in mind this is all going to be live at mains voltage. Ta-da! That is amply bright. You can see a slight shimmer. on the camera, I can't see that slight shimmer. It's fine. Let's zoom up and let's use shimmer vision. Shimmer vision. Energy pulsator star. Right, okay. So now we've done that. Let's now we've seen it light. That's the fun over then. I wonder, will this even show up in the tester? Will it even be able to detect my rough calculation of 3 milliamps? I'm not even sure it will. Let's bring the hoppy meter in and give that a quick blast. So let's plug this in. Slam that down. It says 6 milliamps. 1.5 watts. Oh, power factor is awesome, but that's largely because all the power is being wasted across the resistors. That's actually more than I was expecting. Those resistors could be getting quite toasty. I'm going to have to check that. What is the voltage across those resistors? It's AC. Is this even going to be accurate? I'm not really sure if I'm going to be able to actually measure that accurately, but let's give it a go anyway. Let's turn it to AC volts. I have to say I don't often use this meter on AC volts. That's just indicative of the type of stuff that I do. Let's probe gingerly into here while not trying to make contact with things myself. It's about 60 volts across those resistors. Oh dear. Rightio. Oh, that's a lot. That's actually no, it's not that much. Hold on, let's do the maths. I'm getting roughly 60 volts across those. So I equals V 60 volts divided by the 15k resistor equals 4 milliamps times 60 volts equals. It's on the rating of the resistor. Maybe it would have been better doing that with 20k, 22k resistors or 180k resistors, 18k resistors even better. So now let's take a knife to the back of this. Let's scrape that gel off, that phosphor-loaded gel. And the resistor's not feeling particularly hot, but then they don't have a huge thermal mass. Knife. I need a knife, a big chib. Let's cut towards myself because it just feels better. Oh, that comes off quite easily. Oh, that comes off very easily. Oh, look at that, look at that, look at that. Are you going to be able to see it? Am I going to be able to bring it into focus that you can actually see all those little tracks in there? Just zigzagging backwards and forwards. Hold on. I can do better than this. Where's the magnifying glass that I dropped? That's what it is in the back. So it is, literally. It's a sort of printed metallic conductive ink with the LEDs deposited on and just the little jumps jumped across. That must be quite complicated to make. What's it look like now I've done that? Let's zoom back out and plug that in again. I like the way the little star just came off completely intact. I kind of want to light this. I'd just put it under ultraviolet light now. I could put it under ultraviolet light. This video would just never end if I tried all the experiments I wanted to. Let's power this up and actually, you know what? It's almost like they didn't really need to add that other layer of gel. It doesn't look blue. It probably looks a slightly different colour. No, you know what? It looks more yellowish on this side, but I don't think they actually need to add the other gel because it looks just as white on that side without this, because all you're getting, you're not seeing the LEDs directly, you're only seeing the reflection of the light from the medium, so from the gel phosphor from the other side. So they could actually just have left that off and it gives it a slightly dotty effect. I don't think it would increase the brightness, would it? Let's just lay this across in a random orientation. That seems to subdue it, if anything, doesn't it? You're not really seeing this because it's completely swamped out. Okay. So, as I said, I'm going to demonstrate what happens if you get the original circuitry, this circuitry, and you put a 220k resistor in series with it. So that bit's now coming up. There will be strobing. This is your first warning that there's going to be strobing if you have any epileptic or photosensitive disorders. That's the next bit of video coming up, and there will be another warning before it happens. So that's coming up now. Bonus extra footage, and this is before I've even made the video. This is while the lamp's still intact and it's very dark, because I'm going to warn you that there's now going to be strobing. So brace yourself for strobing, because this is what happens when you put a 220k resistor in series with this lamp. It just pulses like a little star, and the power consumption is not even registering in the meter. The meter is probably going to it's showing nothing. I tell you what, look at the voltage, 233 volts. That is the lowest it's been in quite a while. Do you know why that is? Because everybody's got their heating on. So you can use these as strobing lamps just by putting a resistor in series with them. Never thought about that before. That's quite neat.